Close your eyes and let's drift back to the world of complex physics. As the world quiets down, imagine lying not in your bed, but in a vast invisible web, one made not of threads, but of forces. Gravity, magnetism, electricity, they stretch and tug like cosmic marionette strings. Every breath you take, every twitch of your toe, even the weight of your blanket, is orchestrated by these unseen hands. You're not really lying still. You're hurtling through space on a spinning rock, caught in the ceaseless ballet of celestial mechanics. Tonight, let's wander through the weirdest truths the universe has to offer. Softly, slowly. Hey guys, tonight we fall asleep to physics, the good kind, the kind you absolutely do not need to understand to enjoy. Honestly, you probably won't survive this journey intellectually, but that's okay. Your brain is about to be massaged with metaphysical nonsense until it gives up and dozes off. So before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And as always, let me know your location and what time it is for you in the comments. I read every single one. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You feel it instantly, the pressure of gravity tugging you downward, but you don't fall. You're suspended in a moment, caught between Newton's apple and Einstein's space-time trampoline. Gravity isn't just pulling you, it's warping the very stage beneath you. Time ticks slower on your feet than on your head. That's not a joke. It's measurable. Scientists actually launched atomic clocks on airplanes just to prove it, because why not? But gravity is just the start. Think about the electromagnetic force. It's the reason you don't fall through your bed right now. Your atoms never truly touch anything. You're hovering over the mattress surface at a microscopic level, propped up by repelling electrons like two magnets refusing a hug. Yes, you're levitating, sort of. Now close your imaginary eyes again and float into the strong nuclear force. Nature's bouncer. It keeps your atomic nucleus from exploding into glitter, even though positively charged protons really want to divorce each other. That's love, or nuclear glue, whichever sounds cozier. And then there's the weak nuclear force. Poor thing, constantly forgotten at science fairs. But without it, there'd be no sunlight, no bananas, no radiation to whisper about. It's the backstage hand pulling off miraculous beta decays, while no one claps. But wait, your body is literally a giant collection of electric fields pushing against other electric fields, bathed in gravity, sizzling with weak force interactions, and anchored by strong force bonds. You're not lying still. You're an orchestra of atomic chaos kept in check by physics laws, written before humanity was even a whisper in space. We once thought all forces were distinct, isolated little divas. But the more we learn, the more they look like shades of the same big mood. Some physicists think they're already unified in a cosmic force smoothie that just tastes different depending on the temperature. Scientists still argue whether this grand unified theory is real or just another theoretical mixtape. So tonight, as you melt into your pillow, remember, you are being held together by invisible hands that obey math you've probably never seen and probably don't want to. And that's okay. They're doing their job just fine without you. You cruise gently now, slow motion through space, like you're lying in the back seat of a cosmic Uber. But things are about to get weird. You're speeding up, faster, faster, until light itself starts to complain. Welcome to relativity. Buckle up. Not that it'll help. You're already breaking every rule your high school physics teacher swore by. As you reach speeds near the speed of light, about 300,000 kilometers per second. But who's counting? Time begins to stretch like bubble gum in the sun. To the people you left behind, you're crawling along like a sleepy sloth. But to you, everything feels perfectly normal. It's only when you try to sync your watch with someone back home that things get spicy. Einstein's theory of special relativity tells us time slows down as you go faster. This isn't some sci-fi metaphor, it actually happens. It's called time dilation. And yes, astronauts aboard the International Space Station age ever so slightly slower than us landlubbers. Not enough to skip wrinkles, sadly. But there's more. Space contracts. If you were somehow able to approach light speed, don't try this at home, obviously, the universe would flatten out in front of you like a warped pancake. Distances shrink, clocks tick slower, and all the math you've ever ignored is quietly flipping you off. And don't forget mass. As you speed up, your mass increases. That's right, you get heavier the faster you go. Try explaining that to your bathroom scale. So you glide through this relativistic realm, watching time itself yawn and stretch. A second for you might be a year for someone else. That birthday card you sent, it'll arrive before you wrote it. Don't overthink it. Now let's go bigger. Enter general relativity, the big sibling who doesn't just twist time. It bends space itself. Gravity isn't just pulling things down, it's reshaping the very geometry around you. Think of space-time as a rubber sheet. Toss a bowling ball on it. That's a planet. Smaller things roll toward it, not because they're being pulled, but because the sheet itself is sloped. You, lying in your bed, are technically falling into Earth forever, just sideways fast enough to keep missing. That's what orbit is. Just a gentle, endless fall. Ever heard of gravitational lensing? Light, which usually minds its business and travels in straight lines, actually bends around massive objects like stars or black holes. Imagine a flashlight beam warping around your furniture because the sofa is really heavy. Nature's funhouse mirror. And scientists still argue whether gravity is actually a force at all, or just a byproduct of the way space-time curves, which is kind of like saying, maybe your bed isn't holding you up. It's just confused about where down is. Relativity makes the universe feel like a Salvador Dali painting. Clocks melting, space folding, and light dragging its feet. But for now, you coast through it all peacefully, like a photon taking the scenic route. You're weightless, timeless, and deeply confused, which is the perfect state for sleep, right? You settle deeper into the mattress now, as your atoms begin to fidget, like toddlers on sugar. Welcome to the quantum world, where everything is tiny, twitchy, and entirely too confident in its weirdness. Right now, your pillow is full of particles that don't know where they are. Seriously, electrons, protons, even the air you're breathing, none of them have a fixed position. Instead, they exist as probabilities. They're smeared out like cream cheese on a bagel, only less tasty and far more philosophical. This isn't just theory. It's quantum mechanics, and it's very real. Electrons orbit the nucleus of an atom, not in perfect loops, but in weird clouds of maybe I'm here, maybe I'm not. They don't settle on a location until you observe them. It's like your cat being simultaneously in and out of the fridge until you open the door. This is called the observer effect, and it's not about conscious minds. It's about interaction. The moment something nudges a quantum particle hard enough to measure it, that particle picks a lane. Before that, it's living its best ambiguous life. And while we're here, let's talk about Heisenberg. Not the bald guy from Breaking Bad, the other one. The Heisenberg uncertainty principle says you can't know a particle's position and momentum at the same time. The more precisely you pin down one, the blurrier the other gets. It's like trying to photograph a hummingbird mid-sneeze. Now, don't panic. But every single atom in your body is playing this jittery guessing game right now. You are made of things that don't know where they are or how fast they're going. And yet, you somehow manage to drink tea and scroll through memes. Remarkable. Even more absurd. Particles can tunnel through barriers they shouldn't be able to pass. It's called quantum tunneling. Imagine throwing a tennis ball at a wall, and every now and then, it just appears on the other side. No hole, no damage. Just bloop, success. This is a real thing. It's why the sun shines. Fusion reactions inside stars rely on it to happen at all. And then there's quantum entanglement. Two particles become linked in such a way that one knows what the other is doing instantly, even if they're light years apart. Einstein famously called it spooky action at a distance, which is adorable and also terrifying. Scientists still argue whether this means information can move faster than light, or if the universe just likes messing with us. Right now, for all you know, a particle in your pillow might be quantum entangled with a particle in a rubber duck in Belgium. Sleep tight. All this uncertainty, this jittery nonsense, it's happening beneath your reality. You're built on top of it, like a house sitting on a trampoline during an earthquake. But somehow, it all averages out. The jitter becomes stillness, the chaos becomes calm, and the absurd becomes sort of boring. So let your atoms buzz and blink and tunnel away. You don't need to supervise. They've been doing this dance since the dawn of time, and they haven't exploded you yet. You're floating now, not just through space, but through layers of reality thinner than your last excuse to skip leg day. Welcome to string theory, where particles aren't points, but tiny vibrating strings, and they come with more baggage than your last group chat. In this bizarre realm, everything you think of as a particle, electrons, quarks, neutrinos, is actually a minuscule loop of string. But here's the twist. The vibration pattern of each string determines what kind of particle it is. If it zings one way, it's a photon. Wiggle it differently, and you've got a graviton, the hypothetical particle that carries gravity, which still hasn't RSVP'd to science. It's like the universe is made of violin strings, each note creating a different chunk of matter. Congratulations. You are, fundamentally, a song. A chaotic, cosmic, very out-of-tune song. You probably never ever heard about this, because even physicists argue over whether it makes sense or is just math-induced jazz. But string theory doesn't stop there. Oh no. It demands extra dimensions. Not just the 3 you're used to, or even the 4th if you're counting time. We're talking 10 or 11 dimensions in total. You can't see them, because they're supposedly curled up tighter than last night's anxiety. Imagine a garden hose. From far away, it looks like a one-dimensional line, but up close, you notice it has a tiny circular dimension wrapped around it. These extra dimensions in string theory are like that, hidden, tiny, and possibly mocking us with their complexity. So what do these dimensions do? They help explain forces, masses, even why particles behave the way they do. But they also make physicists stay up at night, staring into microwaves thinking, do I even exist? Scientists still argue whether these extra dimensions are real, useful, or just elegant mathematical filler. And here's a spicy twist. There's more than one version of string theory. Actually, There are 5. It was kind of a mess, until someone realized they were all connected through something called M-theory. No, the M doesn't stand for mystery, mother, or meh, but no one can agree on what it does stand for. Possibly magic. In some versions, our entire universe is a 3D membrane floating in a higher dimensional space, like a soap bubble among other bubbles. If those bubbles collide, big bangs happen, no big deal. Just casually bumping into another universe while brushing your teeth. Some physicists even suggest gravity is so weak compared to other forces because it's leaking into another dimension like water dripping behind your fridge. The best part? This entire theory remains unproven. No one's measured a string. No one's opened a drawer and found a hidden dimension. It's all theoretical, but it's also incredibly beautiful and deeply absurd. So now, as you lie there under your blanket, just know you might be a symphony of vibrating loops stretched across folded dimensions, whispering to alternate realities. And you still forgot to do your laundry. You swirl softly now in the warm froth of existence, a delicate blend of particles, energy, and unearned confidence. You've officially dipped your brain into the universe's cosmic latte. Let's stir it. The universe, as you know it, is roughly 5% normal matter. The stuff you can see, touch, smell, or accidentally stub your toe on. That includes you, your cat, your leftovers, and that IKEA lamp you regret buying. But the other 95%? Total mystery. Invisible forces, undetectable particles. It's like the universe is running on ghost ingredients. Before we float too deep into that existential soup, let's look at what you can understand. Take quarks, for example. These little guys are the building blocks of protons and neutrons, which themselves build atoms, and atoms build, well, you. Quarks come in flavors, yes, flavors, called up, down, strange, charm, top and bottom. Sounds like a rejected boy band lineup. Quarks are held together by gluons, which are actual particles, not glue sticks, sadly. They carry the strong force and basically scream, stay together, at the top of their lungs, inside every atom's nucleus. Without them, you'd fall apart like a sad IKEA shelf with no screws. Now toss in electrons, the sassy little energy surfers orbiting atomic nuclei. They follow rules from quantum mechanics, which, as you know, means they never commit to anything. Your body is mostly space between these particles, like a lot of space. If you compressed all the empty space out of your atoms, you'd be about the size of a grain of rice, a very anxious grain of rice. But what's truly unnerving is the vacuum, the space between the stars, the bits where nothing exists. Turns out that nothing is not nothing. It fizzes with energy, fluctuations, and particles popping in and out of existence like quantum fireflies. Physicists call it the quantum vacuum, and it's basically cosmic static. There's even a theory, called zero-point energy, that says the lowest possible energy state of empty space isn't zero, it's something. That something could, in theory, power the future, break physics, or just gently hum you to sleep. Scientists still argue whether this vacuum energy is responsible for the universe's expansion, or if it's just one more way physics is gaslighting us. And let's not forget antimatter. Every particle has an evil twin. Electrons have positrons, protons have antiprotons. And if you meet your mirror self in an alley, you both explode in a puff of energy. That's called annihilation. Romantic, really. But here's the mystery. When the universe began, matter and antimatter should have cancelled each other out, but they didn't. Somehow, We ended up with more matter than antimatter. Why? No one knows. It's the cosmic version of who finished the milk and didn't say anything. So here you are. 5% understandable atoms, 95% mystery goo, floating in a frothy universe stirred by forces we barely grasp, held together by particles with moods, dancing across a stage built from jittery nothing. And you still managed to spill coffee on your shirt this morning. Impressive. You're sinking deeper now, not just into your mattress, but into the quiet march of time's favorite prank. Entropy. That unstoppable slide into messiness. The cosmic reason why your socks disappear, your toast always lands butter side down, and your room somehow gets dirty without you doing anything. Entropy is the second law of thermodynamics diva. It says that in a closed system, disorder always increases. Always. It's the universe's polite way of saying things fall apart. Get used to it. Think about ice cream. It melts. It doesn't unmelt. That's entropy. Heat spreads out. Energy disperses. Systems crumble into chaos. Your body, your bedroom, your brain, they're all running downhill, energy-wise. But entropy isn't just about messiness. It's also about probability. There are way more disordered states than ordered ones. A deck of shuffled cards. Millions of possibilities. A perfectly ordered deck. Just one. Same with the atoms in your room. There are billions of ways they can look random, and only a few ways they can look neat. The math just isn't on your side. Right now, your body is radiating heat, microwaves, infrared, all sorts of sneaky energy escapes. That's entropy too. You're leaking order into the universe slowly and elegantly, like a melting ice sculpture of a confused sloth. And the universe? It's doing the same thing. Galaxies are spreading out, stars are burning through their fuel, and over unimaginable time spans, all matter will eventually decay into randomness. Heat death, the cold, quiet finale of everything. But don't panic, you've got time. Trillions of years probably, maybe even longer if dark energy keeps being weird, which it will. Scientists still argue whether entropy truly means the universe ends, or if there's some strange reversal waiting beyond the horizon. Spoiler, no one knows. Now for a quirky twist. Life, your life, is basically a weird loophole in entropy. Your cells work tirelessly to maintain order, pumping ions, copying DNA, and cleaning up chemical spills. But this order comes at a cost. You generate even more disorder elsewhere. It's like cleaning your room by shoving everything into the closet. Technically tidier, but entropy still wins. Even thoughts generate heat. Your brain burns calories thinking about how entropy works. So yes, even confusion contributes to the universe's downfall. You're doing great. Want something even weirder? Some physicists think entropy may be tied to the flow of time itself. As in, the reason we remember the past but not the future might be because entropy increases in one direction only. It gives time its arrow. Without entropy, maybe there's no past, no future. Just an eternal present with no pants and no coffee. So tonight, as you doze off under tangled blankets and dreams that fray at the edges, remember, entropy is your constant bedtime companion, softly pulling you, your atoms, your memories, your bedtime snack, toward the great cosmic meh. But hey, at least your room being a mess is now scientifically justified. You drift now in almost perfect stillness. Yet galaxies twirl, stars explode, and entire clusters of matter move like dancers you can't see. Welcome to dark matter's favorite game, cosmic hide and seek. And spoiler alert, you're losing. Dark matter is, by all accounts, invisible. It doesn't emit light, reflect it, absorb it, or answer your texts. But it has mass. It pulls. It shapes. It bends the paths of galaxies like someone's tugging from behind the curtain. We know it's there not because we see it, but because we see what it does. When scientists look at how galaxies spin, they should fly apart. Kind of like if you spun a pizza too fast and the cheese took off. But they don't. Something unseen holds them together. That something is dark matter, and there's a lot of it, like 5 times more than the regular matter you're made of. The stuff that makes up trees, tacos, and Taylor Swift songs, just 5%. The rest is invisible scaffolding holding the universe together. Right now, you're swimming through it. Yep, billions of dark matter particles are streaming through you as you listen, silent, indifferent, ghostly. You can't feel them, detect them, or even sue them for invasion of personal space. They're called WIMPs, weakly interacting massive particles, or at least that's the leading guess. There's also axions, sterile neutrinos, and other names that sound like off-brand Pokemon. Scientists still argue whether dark matter is made of particles at all, or if it's something stranger. Maybe a property of gravity itself, maybe a fudge factor, maybe just the universe's way of keeping secrets. Every once in a while, physicists build enormous detectors deep underground, giant tanks of liquid xenon, wrapped in sensors, buried beneath mountains, all just to catch a single dark matter particle in the act. So far, nada. Zip. The universe is playing hard to get. And yet, dark matter maps out the shape of the cosmos. It seeded galaxies in the early universe. It herd stars like sheepdogs you can't see. Without it, galaxies would be flabby, loose spirals with no rhythm or reason. Kind of like a failed DIY project made of stars. There's even a fringe idea that we might be made of dark matter, like mirror versions of ourselves existing in parallel, untouchable, but gravitationally tangled. Imagine your dark matter self brushing their teeth while you fall asleep, neither of you knowing the other exists. Cozy. Now here's a delightfully unhelpful fact. We've mapped dark matter's effects across billions of light years. We can see it bending light, gravitational lensing again, remember? And shaping the structure of the cosmos. It's like watching footprints appear in fresh snow, but never catching the walker. Frustrating, also oddly poetic. And yet, the hunt goes on. Physicists spend lifetimes chasing particles they've never seen, through experiments that cost millions, to find evidence that might not exist. And honestly, that's kind of beautiful. So sleep easy tonight, knowing that the universe is cradled in invisible arms. You don't need to understand it. You just need to float gently in its grip, the way galaxies do, quietly held together by a mystery. You're circling now, spiraling inward, not toward your pillow, but toward something darker, heavier, and infinitely sassier than anything else in the cosmos. A black hole, the ultimate celestial drama queen. Black holes don't just bend the rules of physics. They demand a full rewrite, throw the book out the window, and then eat the window. These are objects so dense their gravity is absolute. Light itself tries to escape and fails. That's right. Black holes trap light. They're like the universe's nope buttons. Here's how they're born. Take a massive star, let it burn for millions of years, then let it run out of fuel. The outer layers explode in a supernova, a brief, spectacular tantrum. The core collapses under its own weight, and boom, gravity wins. What's left behind is a singularity, a point of infinite density, and an event horizon, the black hole surface of no return. Cross it and you're toast, or more accurately, noodle soup. Scientists call this spaghettification, which sounds cute until you realize it means getting stretched into a long, screaming pasta strand by gravitational forces. Bon appetit. Right now, your galaxy has a black hole at its center. Most galaxies do. Ours is called Sagittarius A, which sounds like a corporate HR department, but is actually 4 million times the mass of the Sun. And it's chill, for now. But black holes aren't just monsters, they're messengers. Their gravitational influence helps shape galaxies. Their collisions send out ripples in space-time itself, gravitational waves. In 2015, scientists finally detected one of these waves. 2 black holes merged over 1 billion light-years away, and the resulting ripple passed through Earth. It moved the arms of LIGO, our gravitational wave detector, by less than the width of a proton. And yes, someone still spilled coffee near it, probably. Here's where things get even messier. Inside a black hole, the laws of physics collapse. Einstein's relativity breaks down. Quantum mechanics panics. Scientists still argue whether information is lost in a black hole or preserved somehow on the event horizon, like data on a cosmic USB stick. This is the infamous black hole information paradox. And it's not just academic. Solving it might unlock the key to unifying gravity with quantum mechanics. Oh, and there's Hawking radiation. Stephen Hawking's cheeky prediction that black holes slowly evaporate over time, leaking tiny bits of energy. If true, black holes eventually vanish, slowly, quietly, like that one friend who ghosts the group chat but still likes your posts. And some people think there might be primordial black holes, ones formed just after the Big Bang, tiny, ancient, and possibly all around us. If they exist, they could even explain dark matter, or cause major problems. You know, the usual science stuff. But for now, you just float near one. Don't worry, not too close. The stars bend, the sky warps, and time itself drips like honey. Everything near the event horizon stretches, slows, distorts. 1 second for you could be 1,000 years outside, and you're just napping through it. Bravo. You hover gently now, in the afterglow of the universe's most powerful divas. But the weirdness hasn't peaked yet. It's time to collapse into the true quantum circus act. Wave-particle duality, where light can't make up its mind, and neither can anything else. Picture a beam of light. Seems simple, right? But shine that beam through 2 narrow slits and suddenly, chaos. Instead of casting 2 neat lines on the wall behind, the light creates a bizarre pattern of bright and dark stripes, an interference pattern. That's a wave thing. Waves do that. Ocean waves, sound waves, your little brother's annoying voice echoing through the house. But here's the twist. Send just 1 photon, 1 tiny particle of light, through the slits, and you still get an interference pattern over time. It's like the photon splits in 2, goes through both slits, interferes with itself, and then lands on the wall pretending it was always 1 tidy unit. Rude. So is light a wave or a particle? Yes. Welcome to wave-particle duality. It's not just for photons either. Electrons, atoms, even entire molecules do this weird dance. Everything at the quantum level has both wave-like and particle-like properties, which is like saying your toaster is also sometimes a trombone, depending on whether you're looking. The truly headache-inducing part, If you try to measure which slit the photon goes through, just watch it. You kill the interference pattern. It picks a slit and acts like a boring old particle again. Observation collapses the wave function. The universe changes behavior based on whether you're paying attention. It's the ultimate diva move. This is what makes quantum mechanics so deeply unsettling. Reality seems probabilistic until someone checks. Before that, everything exists in a fuzzy cloud of possibilities. Schrödinger's cat isn't just a metaphor. It's a full-blown lifestyle. Right now, all around you, particles are surfing probability waves, blinking in and out of coherence like uncertain interns. Your atoms are composed of subatomic bits that constantly decide what they are based on interactions. Even the air in your room, the particles bouncing around your face like tiny, invisible ping-pong balls, are doing the wave-particle waltz. And yes, it applies to you too. You, technically, have a wave function. A really tiny one, granted. You're way too big to notice it. But it's there, theoretically rippling across space. You are simultaneously everywhere and here, until gravity and cheeseburgers pinned you down. Scientists still argue whether the wave function represents physical reality or just our knowledge of it. Are we collapsing real waves or just collapsing our expectations? It's like quantum physics is gaslighting us with math. One fringe idea says consciousness itself might cause wave function collapse. That reality is undefined until a mind looks at it. Another says reality is always defined. We just live in one of many branches where things happened a certain way. Congratulations, you're in the timeline where socks never match. So next time you feel uncertain, just remember, at the quantum level everything is. And somehow, out of all that confusion, came the world you know. Your tea, your toes, your dreams. And now you lie there in the calm glow of this uncertainty, rocked gently by waves you can't see, waiting for your own next collapse into sleep. You're drifting again, this time towards something deceptively simple. 2 slits, a screen, and the collapse of reality as you know it. Yes, we already dipped our toes into wave-particle duality, but now we're diving in head first, because nothing in physics causes more delightful existential dread than the infamous double-slit experiment. Here's the setup. You fire particles, let's say electrons, at a barrier with 2 vertical slits, and you place a screen behind that catches wherever they land. Intuitively, you'd expect 2 clumps, right? One behind each slit. But nope. You get an interference pattern, like ripples from 2 pebbles dropped into a pond. That's a wave thing, meaning each electron acts like it splits and goes through both slits. But wait, fire them one at a time. Single electrons spaced out, days apart, and you still get the same interference pattern over time. Which means each electron is somehow interfering with itself, like it's going through both slits and comparing notes. Rude. Now the real drama. Add a detector to see which slit the electron goes through. The moment you observe the path, the interference pattern disappears. The electron suddenly chooses a slit and behaves like a particle. It's like the universe goes, "Oh, you're watching. I'll behave." It's not a science experiment anymore. It's a cosmic performance. This experiment is so bananas that physicists still argue what it means. Some think it reveals a fundamental link between measurement and reality. Others believe it proves that everything exists in a cloud of overlapping possibilities until observation narrows it down. That's the Copenhagen interpretation, a fancy way of saying don't ask too many questions. Then there's the many worlds interpretation, which refuses to be out-weirded. It says that every possible outcome actually happens, each in its own branching universe. In one, the electron goes left. In another, right. In a third, it becomes a jazz musician. And so on. You, the observer, are also split across those branches, each of you cluelessly living one possible version of the story. It gets better. Some physicists have recreated versions of this experiment using large molecules, whole clusters of atoms, and still found interference. In theory, this bizarre behavior might apply to anything, including cats, sandwiches, maybe even you. The only reason your body doesn't show interference patterns is that it's constantly observed by photons, air molecules, your own nervous system. You're collapsing your own wave function just by existing. Way to be high maintenance. And if your brain hurts right now, that's fine. It should. The double slit experiment isn't meant to be understood. It's meant to haunt your shower thoughts forever. It's the physics version of, what if we're all just simulations, but with math? So here you are, a walking wave packet of probability, collapsing into a single version of reality every second, lying on a bed made of particles that may or may not be in two places at once. And yet, the blanket is warm, the air is still, and somewhere, deep in the math, the universe is still deciding which version of you gets to dream tonight. Time stretches now, not just in seconds and minutes, but in questions. Questions like, what is time, really? Why does it only go forward? And why does waiting in line feel longer than a whole vacation? Time is slippery. You think of it as constant, tick-tock, always forward. But physics, it doesn't care about your schedule. At the deepest levels, most physical laws don't prefer a direction. They're time-symmetric. Run them backward, and they still make sense. A ball flying through the air. That math works the same whether it's rising or falling. But drop a coffee mug and watch it shatter. Now that doesn't rewind neatly. You never see the shards jump back onto the table. So where does this arrow of time come from? Entropy, mostly. As we covered earlier, disorder always increases. That rise in entropy is what gives time its direction. Things move from ordered to chaotic, from ice cubes to puddles, from clean rooms to laundry explosions. Without entropy, time wouldn't have a direction at all. It would just be static. A frozen map of everything, everywhere, all at once. Good movie. Awful physics headache. But time does get weirder. According to Einstein, time is woven into space itself. Together, they form space-time. And space-time can bend. Move faster, and your time slows. Sit near a massive object, like a planet or a black hole, and time also slows. We've measured this with atomic clocks. One on a mountaintop ticks slightly faster than one at sea level. Your head is aging faster than your feet. No offense to your feet. In fact, GPS satellites have to account for this. Their clocks tick faster because they're farther from Earth's gravity, and slower because they're moving quickly. Without correcting for relativity, your phone would be off by kilometers in minutes. And then good luck finding your favorite taco truck. Here's a spicy tidbit. If you could travel at near light speed, time for you would slow to a crawl. Go fast enough, and you could return home to find everyone else aged decades, while you've barely aged at all. It's called time dilation, and it's not just theoretical. It's built into the math of special relativity. But traveling backward in time, that's a whole different beast. The equations technically allow it under very special circumstances, like wormholes or rotating universes. But nature seems to despise time travel paradoxes. The whole go back and squish a butterfly scenario, probably off limits. Scientists still argue whether time loops could exist without ruining causality, or whether the universe just quietly prevents that kind of nonsense with cosmic duct tape. And then there's subjective time, the kind you feel. 10 minutes can be agony in a dentist chair. Dentist chair and a blink when you're watching cat videos. Your brain distorts time constantly, stretching and shrinking moments based on stress, boredom, or joy. So really, there's clock time, space time, and brain time, and good luck syncing all three. So as you settle into this moment, this unrepeatable sliver of the present, remember, time isn't ticking uniformly. It's flowing, bending, stretching, and sometimes, in dreams, it even loops. And somewhere, far away, a lonely clock is ticking at a slightly different pace, just for you. You glide now through the walls, not metaphorically, but literally, if quantum mechanics has anything to say about it. Welcome to quantum tunneling, the polite defiance of barriers by particles that, frankly, couldn't care less about your classical assumptions. Let's say there's a particle, an electron perhaps, trapped in a little potential well, like a marble in a bowl. It doesn't have enough energy to climb out of the bowl. Should be stuck there, right? But sometimes, poof, it appears outside the bowl, without ever climbing over. Not magic, not cheating, just tunneling. This happens because, at the quantum level, particles don't behave like marbles. They're wave functions. And those wave functions don't just stop at barriers, they leak through. There's a tiny chance the particle's wave exists on the other side of the barrier. And if the universe rolls the right quantum dice, it shows up there. No digging required. This process powers the sun. Without quantum tunneling, hydrogen nuclei wouldn't get close enough to fuse into helium. The protons repel each other. Positive charges hate being near other positive charges. But tunneling lets them cheat. They zip through their own energy walls, fuse, and unleash sunlight. That sunrise you watched, brought to you by rule-breaking physics. We've also built entire technologies on this phenomenon. Tunneling microscopes let us image individual atoms. Certain types of semiconductors rely on it. And your body? Tunneling happens in enzymes and cell processes all the time. You're basically a very slow quantum computer wrapped in skin and opinions. Now, zoom out. Imagine every atom in your pillow, each one full of electrons with tiny probabilities of tunneling to nearby spots. They don't often succeed, but over billions of years, even mountains can tunnel, very, very slowly. So maybe your particles are planning a great escape. They're just really patient. Tunneling raises awkward questions too. If particles can skip barriers without energy to climb over, what else can happen that defies classical rules? Could your consciousness tunnel between states? Could black holes leak information this way? Could your leftover sandwich disappear and reappear in your neighbor's fridge? Okay, probably not the sandwich, but scientists still argue whether tunneling is purely probabilistic or whether it hints at something deeper, like hidden variables or even alternate realities trading information behind the curtain. The math works, but the why? That's still a sleepy mystery. And here's the quirky twist. Quantum tunneling breaks classical conservation laws temporarily, but the universe doesn't mind. As long as things settle back into balance quickly, it's like physics gives particles a temporary hall pass. Go ahead, break the rules, but just be cool about it. You, meanwhile, are not tunneling through your wall. Macroscopic objects like you obey classical physics because your wave function is smeared out and tangled with everything. Decoherence kills your quantum dreams. Sorry, but you're built on tunneling. It happens inside your DNA, your neurons, maybe even the faint flicker of your thoughts. It's nature's quiet rebellion, particles ignoring no entry signs, showing up where they shouldn't be. So tonight, as your body rests safely in bed, your particles might be throwing tiny subatomic parties in places they technically shouldn't reach, and you don't even have to clean up afterward. You're curled up now in a universe held together by rules, neatly labeled particles, precise forces, tidy charts. At the heart of it all, the Standard Model, physics' ultimate cheat sheet, also known as everything we kind of understand so far. This diagram, usually found haunting physics classrooms, looks like a bingo card crossed with a nerd's dream journal. It lists all the known fundamental particles that make up reality. Quarks, leptons, bosons. The gang's all here. Each has a unique mass, charge, and role. Together, they form the toolkit for the universe. You've already met some of these characters. Quarks come in 6 flavors: up, down, charm, strange, top, and bottom. Combine 2 or 3, and you get protons and neutrons. They're like Lego bricks, tiny, angry Lego bricks held together by gluons, the bosons responsible for the strong nuclear force. Then there are leptons. The superstar is the electron, which keeps atoms in line and powers your light switches. Electrons have heavier cousins, the muon and the tau. These are like electrons that bulked up for no good reason and then immediately vanished. Alongside them are neutrinos, tiny, nearly massless ghost particles that fly through matter without reacting. Trillions are zipping through your skull as you lie here. Don't worry, they're gentle. And bosons? Those are the force carriers. Photons handle electromagnetism, light, radio, Wi-Fi. Gluons do the strong force. W and Z bosons manage the weak force, which handles radioactive decay and the fact that bananas eventually get gross. Then there's the Higgs boson, the God particle, if you like drama, which gives mass to particles via the Higgs field. Discovered in 2012 after decades of theorizing, it completed the Standard Model like a missing puzzle piece. A shy, extremely heavy puzzle piece. So great. We've got this elegant model. It predicts particle behavior with incredible precision. It's been tested, retested, and tattooed on more than a few physicists. But here's the thing. The Standard Model is kind of tired. It doesn't explain gravity at all. It can't account for dark matter or dark energy, or why neutrinos have mass when it predicted they shouldn't. It also doesn't explain why the Higgs field exists, or why its strength is just right to allow atoms to exist. It's like a car manual that forgets to mention brakes. And worst of all, it has no clue about why the universe contains more matter than antimatter. That's kind of a big one. Scientists still argue whether this imbalance is due to unknown particles, hidden symmetries, or something even stranger. So despite its success, the Standard Model is clearly incomplete. It's like a gorgeous cake that's missing the center. Sweet, structured, but hollow in all the places that matter most. Physicists are trying to extend it. Supersymmetry is one idea. Each particle has a super partner we haven't discovered yet. There's also string theory, which says all particles are vibrating strings in extra dimensions. Or maybe there's a whole new framework waiting just around the corner, scribbled on a napkin in some quiet lab. But for now, we hold on to the standard model, not because it explains everything, but because it explains a lot. Like a beloved old car that doesn't start in winter, but always gets you home when it counts. So sleep soundly, wrapped in a blanket of bosons and built from mismatched quarks, knowing that even if the universe isn't fully understood, it's at least very well categorized. You sink even deeper now, cozy and heavy, not unlike the force pulling everything toward the floor. Gravity, the OG of physics, the apple falling, moon orbiting, back pain causing force that has shaped the universe since, well, forever. But here's the weird part. We still don't really understand it. Gravity seems simple on the surface. Newton gave us the classic version. Two objects pull on each other with a force proportional to their masses and inversely proportional to the square of the distance between them. Apples fall, planets orbit, bridges don't collapse. It was neat, tidy, and got humanity to the moon. Then came Einstein, and he broke gravity open like a cosmic piñata. In general relativity, gravity isn't a force, but the warping of space-time itself. Massive objects bend space, and other things move along the curves. You're not being pulled to the Earth's surface. You're following the curve of space-time created by Earth's mass. It's like being on a giant, invisible trampoline that refuses to explain itself. But even with Einstein's elegant equations, gravity remains the glitch in the matrix. It's absurdly weak. Seriously. The electromagnetic force is about 1036 times stronger. You can lift a paperclip with a tiny magnet and defeat the entire gravitational pull of the planet. Embarrassing. Why is gravity so weak? Scientists still argue about it. Maybe gravity leaks into extra dimensions. Maybe we're only seeing part of it. Or maybe, just maybe, gravity isn't a fundamental force at all. Some theories suggest it could be an emergent property, like temperature or pressure, something that only appears when a lot of stuff is interacting. The universe is shady like that. And then there's quantum gravity, the holy grail of modern physics. We've got great theories for the very small, quantum mechanics, and the very large, general relativity. But they hate each other. Mash them together, and the math breaks like IKEA furniture under stress. We have no working quantum theory of gravity. String theory and loop quantum gravity are top contenders, but nobody's cracked the code. We think there's a graviton, a hypothetical particle that carries the gravitational force, but we've never found one. Gravity is just too soft-spoken. It doesn't slam into detectors like other particles. It whispers from the background, bends light, and curves time without ever showing its face. Meanwhile, black holes, gravity's moodiest expression, push the force to extremes. At their center is a singularity, infinite density, zero volume, and math that screams in protest. No one knows what happens inside. Time might stop, reality might invert, your dreams might get a new wardrobe. Even gravity waves, those ripples in space-time from merging black holes, were only detected in 2015. We've been listening to the cosmos for centuries and only recently realized it's humming. And yet, gravity affects everything. It shaped the stars. It sculpted galaxies. It holds your butt in bed. It decides the fate of the universe itself, whether we keep expanding, slow down, or collapse in a cosmic shrug called the Big Crunch. So tonight, as you lie still, gravity is tucking you in, softly, silently, unrelentingly. You're gently glued to Earth, spinning through space at 1,000 miles per hour, never flung off, never flailing. And still, scientists are trying to figure out what gravity really is. Good luck to them. You've got better things to do, like sleep. You're featherlight now, drifting through a sea of particles that aren't quite particles, not exactly waves, and definitely not what your high school textbook promised. Because, let's be honest, particles, they're just vibes. Let's start with the basics. Every bit of matter in your body, every proton, neutron, and electron, is what we call a particle. But in the world of quantum field theory, particles are actually excitations in fields. That's right. Fields are the real MVPs. Particles are just temporary spikes in those fields, like little localized boops of energy. A photon, just a ripple in the electromagnetic field. An electron, a ripple in the electron field. In other words, you're made of temporary ripples in overlapping invisible fields that stretch across the universe. You're a pattern, a vibration, a highly organized collection of twitchy, energetic moods. No wonder you're tired. And these particles, these little mood blips, come in two major categories: fermions and bosons. Fermions are the antisocial ones. They include electrons, protons, made of quarks, and neutrons. Fermions follow the Pauli exclusion principle, which says no two of us can be in the same state at the same time. It's like a cosmic assigned seating rule. This is why matter has structure. It's why you don't fall through your chair, and why your atoms stay organized instead of turning into one giant blob of disappointment. Bosons, on the other hand, are party animals. They include photons, gluons, and the Higgs boson. Bosons don't mind sharing states. In fact, they love it. Pack as many together as you want. This is how lasers work. A bunch of photons in perfect synchrony, shining like the universe's karaoke spotlight. And bosons are force carriers. They mediate the four fundamental forces: photons for electromagnetism, gluons for the strong force, W and Z bosons for the weak force, and the ever-elusive graviton for gravity, still MIA, but believed to be fashionably late. So what about your particles? They don't just sit in place, they fluctuate, they interact. They feel other fields and get their properties from those interactions. An electron only has mass because of its coupling with the Higgs field. No Higgs, no mass. Just floaty bits flying through space like confused snowflakes. And let's not forget particle-wave duality. These entities are both particle-like and wave-like. The duality isn't just a trick, it's what they are. Spread out probabilities that collapse into something definite when observed. Like a shy performer who only sings when no one's looking. Here's a delicious twist. Some physicists suggest that particles don't exist at all, at least not in the classical sense. They're just convenient ways to describe interactions in fields. So when you hear particle, think localized field disturbance, which, coincidentally, is also how most toddlers behave. And of course, scientists still argue whether particles are fundamental, or whether they're just emergent properties of even deeper, unknown physics. Like ripples on a pond hiding a greater, unseen ocean beneath. So tonight, as you lie there, remember, you're not made of solid matter. You're a carefully choreographed arrangement of vibrations in invisible fields. You're not just in the universe. You are the universe, briefly vibrating in one particular shape. Now close your eyes and let your vibe settle into something slow, still, and deeply asleep. You slide sideways now, not through space, but through possibility. Through layers upon layers of might-have-beens, almost was-as, and could still be's. Welcome to the multiverse. where your alternate selves are probably doing something way cooler or way dumber than you are right now. The idea is simple and wildly unprovable. What if there's more than one universe? Not just a big, empty somewhere out there, but an entire infinity of universes, each with different versions of physics, timelines, or even you. Some scientists think it's not just a sci-fi trope. It might be reality. One version of it, anyway. Let's start with quantum mechanics, because of course we are. According to the many worlds interpretation, every time a quantum decision happens, a photon goes left or right, an atom decays now or later, the universe splits. One version for each possible outcome. Every coin flip, every Schrodinger's cat, every awkward text you almost sent but didn't. All of it happened. Somewhere else. In one universe you're asleep. In another you got up for a midnight snack. In another you became a llama. Why not? The math doesn't stop you. But wait, there's more. Cosmic inflation. The rapid expansion after the Big Bang may have created bubble universes. Each bubble contains a different universe, possibly with different physical laws. Gravity might be stronger. Electrons might not exist. Pineapples might be sentient. It's not just, what if history went differently? It's, what if the fundamental fabric of everything was totally retextured? And let's not forget string theory's contribution. It suggests extra dimensions, curled up, hidden little realms beyond our senses. Some versions allow for brain worlds, where our universe is a 3D membrane floating in a higher dimensional space, next to other parallel membranes. Occasionally, they might collide. Some theories suggest our own Big Bang was the result of such a bump. Scientists still argue whether these ideas are testable. Some say the math demands multiverses. Others say they're philosophical decorations with no observable proof. But if the universe is infinite, and we have good reason to believe it might be, then it could repeat infinitely. Every possible arrangement of atoms, including you, is not just possible, but inevitable. That's right. Somewhere out there, there's another version of you. Actually, an infinite number of them. One had cereal for dinner. One never got that haircut. One is probably doing this exact thing. Lying in bed, listening to a sleepy voice explain that reality is weird. But here's the cozy twist. In this universe, this timeline, this very moment, you are here. Your atoms settled into this specific configuration. You're vibrating in this field, wrapped in this blanket, in this particular version of a cosmos that could have gone a million other ways. So rest easy. No need to worry about the versions of you juggling flaming swords or becoming galactic emperors. They've got their own problems. You've got gravity, a mattress, and a soft whisper telling you that somewhere, somehow, the universe decided this you was worth making. And honestly, that's kind of beautiful. You drift now through patterns. Soft, mathematical lace stretched across the bones of the universe. Look closely, and you'll see it. Symmetry. Not just in flowers or faces, but in particles, fields, forces. The universe, it turns out, loves a good design. Symmetry in physics means something stays the same under transformation. Rotate it, flip it, shift it. If the laws of physics don't change, that's symmetry. And it's everywhere. Without it, nothing would work. Not atoms, not motion, not your ability to reach for snacks in the dark without knocking everything over. There's rotational symmetry. Spin around and gravity still pulls straight down. There's translational symmetry. Move 5 feet to the left, and Newton's laws don't rewrite themselves. There's even time symmetry. Physics doesn't care whether an experiment happens now or later, unless, of course, entropy decides to ruin that idea. But here's where it gets powerful. Symmetry isn't just pretty. It creates conservation laws. Emmy Noether, an actual superhero disguised as a mathematician, showed that for every symmetry in nature, there's a quantity that's conserved. Time symmetry, energy is conserved. Space symmetry, momentum. It's like the universe has a set of locked cabinets labeled "Do Not Lose." That's why a spinning figure skater speeds up when they pull in their arms. Angular momentum, born of rotational symmetry, must stay constant. Noether's theorem ties the universe's gracefulness to its rules. And yes, it's okay to cry a little. It's that elegant. But symmetry isn't just physical, it's fundamental. The standard model we talked about earlier, built almost entirely on symmetry principles. Particles behave the way they do because of gauge symmetries, fancy internal symmetries that dictate how forces operate. Electromagnetism, symmetry. The weak force, more symmetry. Strong force. Yep, you guessed it. Even the Higgs mechanism, the thing that gives particles mass, is about broken symmetry. Imagine a perfect field, uniform in every direction. But one random twitch, one choice, breaks that symmetry, and particles start behaving differently. Some get mass, some don't. The field didn't change. We just picked a direction. It's like a dance floor, where everyone suddenly starts moonwalking, and no one questions it. Symmetry breaking is everywhere. Snowflakes form, crystals grow, and eggs refuse to unscramble, all because perfect order cracked just a little. And scientists still argue whether symmetry is the universe's foundation or just a clever illusion. Is the cosmos built on perfect equations with tiny flaws? Or is the chaos hiding a deeper, unseen balance? Now here's the quirky bit. Some physicists think the universe used to have perfect symmetry, a moment after the Big Bang, before things cooled and split into different forces, like one superforce that fractured into gravity, electromagnetism, and the nuclear forces. If true, then everything we see today is a shattered mirror of an original perfection. And you're part of that symmetry. Your body is a bilaterally symmetrical structure. Your cells follow conserved rules. Even your heartbeat has rhythm, balance, cadence. The universe is not just outside you, it's in you. Symmetry lives in your breath, your blink, the quiet rise and fall of your thoughts. So tonight, as you lie in stillness, feel the symmetry around you, in the pulse of time, in the silence between stars, in the patterns that hold it all together, seen or unseen. And if one day you wake up feeling just a little off, that's okay. Even the universe breaks symmetry sometimes. You lie still now, but your body is under siege, not by noise or light or even existential dread, but by neutrinos, billions of them, streaming through your body every second, through your pillow, through the earth itself. Ghosts in the particle world, and they do not care. Neutrinos are famously aloof. They have almost no mass, no electric charge, and barely interact with anything. You could shoot a beam of neutrinos through a light year of solid lead, and most would pass through without even noticing. They're the introverts of the particle world, quiet, distant, and probably judging us all. Where do they come from? Everywhere. The sun produces trillions every second. So do nuclear reactions, radioactive decay, and the occasional supernova having a tantrum on the other side of the galaxy. Even bananas emit neutrinos as their potassium quietly breaks down. So yes, that smoothie you had earlier was ever so slightly radioactive. You're welcome. Despite their shyness, neutrinos matter, literally. Their sheer number makes them a significant piece of the universe's mass budget, and they hold clues to some of the deepest mysteries in physics, like why there's more matter than antimatter, or how the early universe evolved, or whether we're living inside some vast, particle-based soap opera. For decades, physicists assumed neutrinos were massless because they're so whatever. But then they noticed something strange. Neutrinos change types. There are 3 flavors: electron, muon, and tau, and they morph between them mid-flight. This flavor oscillation only makes sense if neutrinos have mass. So surprise, they do. Just very, very little. Like, we had to invent new detectors and bury them under mountains. Little. These detectors are often giant underground tanks filled with ultra-pure water or ice, just sitting there, waiting for a neutrino to say hi. When one finally bumps into something, and it's rare, a tiny flash of light gives it away. It's like listening for a single raindrop in the middle of a desert storm. And then there's the fringe stuff. Some theories suggest a 4th type of neutrino, the sterile neutrino, even more antisocial than the others. It wouldn't interact via any known force, only gravity. Scientists still argue whether it exists, or if it's just a cosmic rumor started by particularly bored researchers. Some even wonder if neutrinos could be connected to dark matter, or if they violate CP symmetry, a kind of mathematical fairness between matter and antimatter, which could help explain why the universe isn't just a blank nothing after the Big Bang. Neutrinos might be the quiet revolutionaries of physics, changing everything without making a sound. Right now, you're being hit by about 65 billion solar neutrinos per square centimeter of your body every second, and they pass through like you're not even there. No tingles, no sparkle, just quiet persistence. They're the cosmic background chatter we only recently learned how to listen to. So as you fall deeper into sleep, remember, the universe is whispering to you in neutrinos, old ones from distant stars, fresh ones from your own lunch, all of them passing through, unnoticed, like the dreams that flutter across your brain. You are not alone, not ever. The ghost particles are always there, drifting silently through everything, and somehow that makes the night feel even quieter. You've grown weightless now, suspended not in the air, but in mass, or rather in the mystery of it, because, strange as it sounds, mass isn't something your particles just have. It's something they get from an invisible field you can't see, touch, or scream at during rush hour traffic. Welcome to the Higgs field, the molasses of existence. Picture the universe right after the Big Bang, hot, chaotic, particles zooming around like unsupervised toddlers. None of them had mass. They were fast, wild, untethered. But as things cooled, a field began to form, pervasive, omnipresent, like fog, or glitter, or clingy vibes. This was the Higgs field, and as particles moved through it, some got tangled up. The more they interacted with the field, the more mass they acquired. It's like walking through a crowded room. Some of you glide through unnoticed, others get mobbed for selfies. That resistance is what we call mass, not because the particles are heavy in some absolute sense, but because they're slowed down by their interaction with the field. The photon glides right through, no mass. The W and Z bosons, they get majorly stuck. Electrons, just enough mass to orbit atoms but not ruin dinner. Now, the Higgs boson is the quantum particle linked to this field. Think of it as a ripple in the Higgs field, just like a photon is a ripple in the electromagnetic field. For decades, it was the missing piece of the standard model puzzle. We needed it to explain why particles had mass, but we couldn't find it. Then, in 2012, boom, the Large Hadron Collider at CERN finally spotted it. A brief flash, a tiny bump in the data, and decades of theory were suddenly vindicated. Scientists cried, Twitter freaked out, and the boson got the world's most confusing nickname, the God particle, which the physicists hated, but the media adored. But even with its discovery, the Higgs still raises questions. Why does it have the mass it has? Why is the Higgs field strength exactly what it is? Just enough to allow atoms, stars, and puppies to exist, but not so strong that everything collapses into black holes. Scientists still argue whether this delicate balance is pure coincidence, or evidence of something deeper, a multiverse, a hidden symmetry, a cosmic tuning dial turned just so. And then there's the odd behavior of the Higgs field itself. It's not like other fields. It has a non-zero value even in empty space. That's right. Even in the vacuum of nothing, the Higgs field is on. It's like a radio station that never shuts off, humming its frequency into every corner of space-time. Right now, as you rest, every atom in your body is humming with mass. Not because it wants to, but because it's constantly wading through the Higgs field. Like a swimmer in honey, slow and dignified. Your mass is your resistance. Your weight is just gravity's reaction to that resistance. Your entire physical presence is just your particles trying to walk through the cosmic fog. And you didn't even ask for it. So as you lie there, perfectly heavy in your blanket nest, just know your existence is the result of a cosmic field that decided to thicken space and hand out inertia. You don't need to thank it. Just sleep on it. You float now in the deep hush of understanding, a starlit bath of math, mass, and mystery. But every journey has its final destination, and tonight we drift toward the quietest of them all, the heat death of the universe. Sounds ominous. Don't worry. It's the most peaceful apocalypse you could imagine. Let's rewind one last time. The universe is expanding, stretching space itself, like taffy that never snaps. Galaxies are racing away from each other faster and faster. That's thanks to dark energy, the sneaky force accelerating this growth. And as the universe expands, it cools, spreads out, becomes emptier. Over time, stars burn out. Gas clouds fade. Black holes evaporate via Hawking radiation. Yes, even those monstrous gravity wells eventually whisper themselves out of existence. And what are we left with? Not fire and brimstone, not explosions or collapses, just stillness. The heat death is what happens when everything useful, every source of energy, has been spent. Entropy reaches its maximum. No more stars to burn. No more gradients for heat to flow. Just a cold, thin soup of photons and low-energy particles drifting endlessly. No structure, no contrast, just equilibrium, forever. But here's the cozy part. It's not violent. It's not scary. It's the softest end imaginable. The universe doesn't crash. It fades. Like a lullaby slowly losing its melody. Like your favorite blanket wearing thin at the corners. Scientists still argue whether this is truly the end, or if new physics might stir things up again in the far, far future. Maybe quantum fluctuations will spark baby universes. Maybe entropy resets. Maybe this quiet ending is just the prologue to another weird, wild beginning. But in our current understanding, the heat death is the final curtain, the ultimate do not disturb. And oddly, it's kind of beautiful. Because you, listening here now, exist at the universe's prime. Stars are still burning. Life still thrives. You're alive in the cosmic blink where complexity dances, where particles still bother interacting, where brains like yours can wonder, dream, and yes, get a little sleepy. So tonight, as the final images swirl through your thoughts, picture the future not as something to fear, but something vast and slow. A quiet sea with no storms, a final hush stretched across time. And know that your atoms came from stars. Your thoughts are vibrations in fields, and your sleep is the universe's favorite function, rest. And now, breathe a little deeper. Let your mind settle. Let every odd particle, every tangled theory, every bent law of physics fade softly into the distance. The stars still shine. The fields still hum. But for now, there's nothing more to solve. You are safe. You are still. The universe continues its slow, mysterious waltz, and you, for this quiet moment, can simply float. Let the hush of heat death cradle your dreams like starlight in velvet. No more questions, no more forces, just you, your breath, and a night sky full of possibility.